Can you hear me online? Can you hear me? Right, so we were looking at virtual address spaces. So once again, this is the virtual address space of a Linux process, and this is entirely an illusion. And we manage this virtual address space. The kernel manages this virtual address space using a bunch of data structures. There's nothing else but a bunch of data structures to tell the kernel which areas of virtual memory or which segments of virtual memory has been allocated by the user and which are free. And we can arbitrarily divide the areas into whatever we want to call them, however we want to use them. But this is for uniformity, for portability. We have defined a few areas here, user stack, kernel code, and data, runtime heap, and we place them for each process at exactly the same address or location for uniformity and to make it easy for tools, compilers, linkers to target compilation of programs. And this is how the data structures look like. It is not the intention of this course to start teaching you about the insides of the kernel and what the data structures are and what they look like. The only thing we want to tell you here is that it is just a bunch of data structures. There is no such thing as a 4 GB virtual address space in physical memory. It is actually stored on disk, and we use the data structures to remember which areas are mapped and which are not. And there are other flags, protection bits, and all that to tell the kernel which process has permission to read what areas of virtual address space. We looked at the page fault handling. If the page fault handler finds out that a read of an address is in an area which is not mapped, it will generate a segmentation fault. Virtual memory areas are also called segments. This is just a different terminology. And segmentation fault that you might have seen in the labs is when you're trying to access an area page in an area that the user has not allocated. So it's a this is a scenario where you do something wrong with your pointer arithmetic. You might try to write, a user process might try to write in an area for which it does not have write permissions, and there is a general protection exception, and then there is the normal page fault that the kernel will try to do the normal mapping of virtual page to physical page and bring something from disk and choose a victim page and all that. So we were looking at memory mappings, and there are two types. We can initialize an area of virtual memory, any area we want, any unallocated area, we can map it and we can back it by a file on disk, a regular file. A file is nothing but a bunch of bytes representing anything that the user wants. It could be a database, it could be a photo, whatever. This is one type of mapping, and the second type of mapping is anonymous mapping. This is where the kernel maintains a special zero file. This file has nothing but zeros. It's in physical memory, and this is called an anonymous file. So you can map a virtual area to disk, to a file on disk, or to an anonymous file. So we can create a memory mapping by initializing, by associating with disk objects, and we can back the area by regular file or anonymous file. Now, regular file is something that is stored on disk, as I was saying, and anonymous file is a special case where the user process does not want to map the virtual area and back it by disk, by a file, but the user just wants a bunch of pages to use for data structures and for other program data. So, and we call it an anonymous file. So for instance, when you have a program and you want to create a data structure on the heap, right? You can create a mapping in the virtual address space, and you can reserve some pages in your heap that are initially 0. And then you can do something with those pages. You can create data structures, arrays, linked lists on those pages. In such a case, there is no memory transfer. There is no transfer between memory and disk. And initially, the page is just a bunch of zeros. So we call these demand zero pages. And once the process tries to write the page, it becomes like any other page. So initially, the kernel only allocates the page, the virtual pages. The kernel only, in its data structures, take a note that this virtual memory area has been reserved or allocated by the user. And the page table entries point to an anonymous file. Now, anonymous file could be just a page with a bunch of zeros that the kernel maintains in physical memory for special purposes. And once there is a fault, when there is an access to this page, the page hasn't been, a physical page hasn't been allocated for this virtual page. There's a page fault. The page fault handler will try to find a physical page that is free. And the next thing the page fault handler will do is, what will the page fault handler do? What are we missing at this point? So let's say we find a physical page. We have reserved the virtual area, this area in the virtual address space. There is a page fault. The page fault handler will find a physical page for us. And what will happen next? What is the thing that the page fault handler needs to do? We need a virtual to physical mapping. So the kernel or the page fault handler will then fix the V to P mapping in the page table entry for this page. And because this is an anonymous page, there is no need to bring something from disk. That is the important thing. So this page is not backed by a file, by a regular file. We can create a mapping where we back the page by an actual file. In that case, when there is a page fault, the kernel will actually need to bring the page from disk. But with anonymous mapping, this does not happen. And pages are backed by, if we run out of physical memory, all pages are backed by a special file called swap file, where the operating system saves pages that cannot fit in physical memory. Note that this is only true for anonymous pages. If you back a mapping by a file, then you write to the file. But anonymous pages don't have a backing file on disk, so the kernel will write them to a special file called the swap file. You might have heard of swapping in your laptops and other machines that you use. Okay, so we have a virtual address space. We know what a virtual address space is. We can create an arbitrary mapping in this virtual address space. We can reserve a portion, an area in this virtual address space. And we can back it either by a regular file that physically exists on disk, and we can use the page fault mechanism to bring portions of that file into physical memory. If we don't want to do that, if we are not interested in actually accessing a file on disk, we can create an anonymous mapping. And this anonymous mapping, initially, all the page table entries in this special area will point to a zero file, which is just a zeroed physical page that the kernel has. And all the protection bits, everything will be zero. When there is a fault, the operating system will then find a page in physical memory and fix the mapping for us. And this is important because when we create data structures on the heap, when you are writing your memory allocator in the labs, you are creating a virtual mapping. You're creating a new mapping in your virtual address space, and then you're writing your allocator to manage that. In this case, there is no need for any transfer between disk and memory. This is just in memory. You're just managing pages in physical memory, right? So this is more of an optimization. We can use virtual memory for sharing. So here we have two processes, process A and process B. And we have a shared object. An object is anything on disk, a file or something. And this process has mapped this object in its virtual address space. This is a virtual space, okay? This is some address, A, B, whatever, okay? And this is mapped to a shared object on disk, and the kernel will bring it in physical memory when there is a page fault. In this case, this is not an anonymous object. This is an actual file that is on disk. The second process can map the same object in its virtual address space. At an arbitrary virtual address, these virtual addresses don't need to be the same. This process can map this shared object anywhere in its virtual address space, starting from B, and this process can map in physical memory, there needs only be one copy of the object. So the object or a file is on disk. When there is a page fault, the kernel will realize that it needs to bring something from disk into physical memory. It will bring a copy of this shared object in physical memory. When the second process maps the same object, the kernel is smart enough to know that this object is already in physical memory. So there's no need to bring two copies. What is a good example of where we use this in our systems? How do we benefit from this shared objects? Is there an example where different programs that you're writing in the labs are using some shared pre-written data structures and functions? So the standard C library is an example. All programs use the standard C library. And once the library is compiled, once the functions are compiled, if your 100 processes running on your system, they will all need to use the shared library, shared C library. And this is where shared objects are really useful. You don't need to bring one copy of C library in physical memory for each process. You need to bring one once the executable or the executed or the binary object representing the C library, compiled and everything. And all processes will share one copy of that in physical memory. And they can map it anywhere they want in their virtual address space. The translation from virtual to physical address spaces will take care of where the actual shared object is in memory. Processes can also map a virtual area as private copy on write. So here we have a virtual area. Process 1 has mapped the shared object. Process 1 maps the object as private copy on write. Okay, and it ends up in physical memory when there's a page fault. A second process maps the same object as private copy on write. And this area is flagged as copy on write in the kernel data structures, and the PDEs are all flagged read-only. So here we are trying to, two processes are accessing the same object, but they probably have the intention to do something special with this object. And each process probably wants to do something different than the other process. And they don't want their changes to be seen by the other process. They want their changes to stay private. So they want to start, so two processes want to start with the same copy of the object, but then they want to do something different with the object. So when there is a write to such an object, the kernel actually creates a copy of the pages in physical memory for each process. So instruction writing to private page triggers a protection fault because initially all the PTEs are flagged as read-only. So when the kernel sees a write, or when there is a write to such a page, there's a protection fault, and the handler creates a new read-write page. And each process will now have its own copy of the pages that it's writing. So we start with probably a very huge shared object on disk. It's brought in physical memory. And when processes update or write special pages in this object and flag it as a private copy on write, the kernel will actually create copies of those pages. So this happens often when processes start with one copy of the object, but they want to do something different without making their changes appear on disk or becoming visible to the other process. So now we have enough knowledge to understand what was really happening in the fork function a few weeks ago. So when we were doing fork, we were saying that the entire virtual address space of the process is copied and handed over to the child process. But now we know that there is no such thing as, actual virtual address space in memory. It's just a bunch of data structures. So to create a virtual address space for a new process, the kernel creates exact copies of the struct, VM area struct, and page tables. And in both processes, the pages are flagged as read-only. And in the VM area struct, the processes are flagged as private copy on write. So when fork returns, each process, the parent process and the child process, has an exact copy of virtual memory. So we just copy their data structures of the parent process, and we allocate those data structures for the child process. We flag the page table entries or the pages as read-only, and the VM area struct as private copy on write. Now, what happens if the child process performs a write to one of the pages that it inherits from the parent? Right. There will be a protection fault, and the child will get its own copy of the virtual. Child will get its own copy of the page in physical memory. Parent will not see the changes to the page that the kernel gives to the child process. So this is how we actually, it's really very simple. There is no need to copy 4 GB anywhere from anywhere. You just replicate the data structures, you flag them as read-only, you flag the VM area as copy on write, and when there is an actual write by the child process just gets a new copy of the page in physical memory. And what about the virtual to physical mapping of this new page for the child process? The kernel will update the virtual to physical mapping, so the child process now sees the new page in physical memory, and not the page that it inherited from the parent. Okay, so this is a similar self-study. There's nothing special here. So you have used the mmap function in the labs. So we use the mmap function. It's actually a system call. We use the mmap system call to create a new new mapping in the virtual address space. And this system call allows you to, once again, the term I'm using it is, so you have a memory mapping. What I'm saying is, backed by disk file or anonymous page or anonymous file. Let's just say anonymous. Anonymous file is nothing, just a bunch of zeros. Initially, the page table entries all point to this zero file. And when there is an actual write, the operating system finds a page and actually gives the processor page. So mmap allows you to create both type of mappings. Can someone tell me what actually is a good use of the first type of mapping? Why would you map an area in virtual memory? Why would you back it by disk, by a file on disk? You want to read and write file on disk. There is a 3 characters. In 3 characters, can you say what it is? Separated, 2 characters separated by a slash. IO. Memory mapped IO. Memory mapped file IO. We haven't talked about IO yet in this course. Input, output. Well, we've seen the IO bridge and all that. We know that processor has direct access to physical memory, but we need to do something special to bring something from an IO device, a storage disk, the lecture where the spindle and the arm and everything. Well, this is one way to do IO. We can create a memory mapping using the mmap function. We can back the mapping by a file on disk, and we're done. The kernel will take care of the rest. When there is a page fault, the kernel will have enough information. Hey, there is a page fault. Okay, let me see. This is a virtual address. I need to find a physical page. Okay, here's the victim page. And I need to bring a page from disk, right? And that page belongs to a file on disk. And then the OS will transparently do the input output. It will send some message to the disk, bring the page, and inform the process, I have finished bringing the page. So this is one way to do IO. Applications can use mmap to create a mapping in the virtual address space, back that mapping by a file on disk, and have this illusion that everything is just memory and pointers. Okay, mmap returns a pointer to a newly allocated area in the virtual address space. And programmers can use this pointer to access both anonymous files or regular files. There is no distinction. mmap eliminates this distinction by giving programmers one abstraction, a pointer to this new mapping. And the OS will take care of everything. If it's an anonymous file, the OS will know, hey, there is nothing on this. This is just a bunch of zeros. The program probably wants to use this mapping for heap data structures, arrays, linked lists, trees, stuff like that. Or the kernel will see, hey, this page is backed by actual file. I need to bring something from disk. And programmers can just use pointers to do both things. This is a very powerful abstraction. mmap is very important to understand. Now, you could give a starting address yourself. But programmers typically don't bother with that. To figure out, what address to give when creating a mapping, you really don't care. So 0 means you tell the kernel, pick an address you like, right? The kernel can pick whatever address it likes and just return you the pointer. You can set the protection bits to read only, write only. And the flags, once again, this is anonymous, this is private, this is shared. So you can say map anonymous, right, or right, this is special. Anonymous is, we've been talking about that. Private is when you want to back the mapping by disk, but want it to be private. So your changes don't reflect on the file on disk. Or you can create a shared mapping where you back the file, you back the mapping by disk, and you create a shared mapping. In this case, anything you do is visible to both any other process that has mapped the file or the actual file on disk. So after you call mmap, what happens, this is your virtual address space again, starting from 0 to 4 GB. This is the illusion that you have created, or the kernel has created for you. You map this many bytes, starting at this offset. Sorry. So it's the opposite. This is the virtual memory, and this is the disk file specified by, okay, there's an important thing here. Sorry, this is the virtual memory. This is the illusion that you have created. So you're creating a new mapping in your virtual address space, which is of, this is how big the mapping is. You specify it here. Start address is here or chosen by the kernel, okay? And it grows upward. And you're creating this mapping using mmap. Here we are assuming that this is not map anonymous, this is map, let's say, shared. Now this here tells the kernel if this mapping is backed by an actual file, we need to tell the kernel what file it is. How do we do that? We never use names. We don't use path names and stuff like that in system calls. It's very inefficient and error prone. We use descriptors. We use, the word is descriptor. And it's just an integer. And when we talk about files, we say a file descriptor. And it's just an integer. You tell the kernel, hey, here's the path name, here's the file name, hand me a descriptor, and the OS will give you 2, 3, 4, 5, 6, whatever. And from that point on, you'll never use the path name or the file name again. You use the descriptor and the OS will know what you're talking about, okay? How we create descriptors is something we won't do today, maybe tomorrow, maybe after the break. But this is what a file descriptor is. We don't want to make system calls, write our programs where we are 20 times we are writing the path name of a specific file that we are interested in. For once, at the beginning of the program, we ask the kernel, for this file, hand me a descriptor. Descriptor is just a general term. When we talk about files, we call it a file descriptor. Descriptor means something that describes summarizes a file. It's a summary of a file. And a kernel just hands you, hey, take this, keep this with you, 7. Remember yourself that this path name and this file name is number 7. And whenever you talk to me and you tell me this number, I know what you're talking about. So this is that file descriptor. So when we use the mmap system call, we can either specify the file descriptor, or we can set it to okay, I have to double check what exactly it is for anonymous. If it's an anonymous file, it's either 0 or -1. It depends on from kernel to kernel. I will clarify that later. If you are mapping, creating a mapping, anonymous mapping, then you can just set it to 0 or -1. One of the two. I forgot which one it is exactly, depending on what kernel it is. And then the kernel will know that, okay, this mapping that the user is creating is not backed by any file on this. It's just a anonymous mapping. And it will create an anonymous mapping for you, initially backed by a 0 page. And as you perform accesses on that page, it will actually fix the mappings and find a physical page for you. If you open a file and you get a file descriptor from the kernel and you have another number here, anything, which is an actual file descriptor describing an actual file that is stored on disk, then the OS will actually map the area and back it by this actual file. This could be anything. And this is a very powerful way to do I/O, input-output. So the programmer can now use this pointer to access files the same way the programmer uses pointers to create arrays, access arrays, linked lists, structures. Okay, so we can. So once again, we don't care about this. We let the kernel decide. Now, we let the kernel decide 0. This is something you know. If you are creating a mapping which is backed by actual file, you as a user know the length of the file. So you can tell the kernel, create a mapping of file size. Let's say you know the size of the file. If you don't know the file size and you're creating an anonymous mapping, in that case, you still know how big of an area you want. So in your labs, in lab 5 or 6, I think every time you call mmap, how big of a chunk you get from mmap? Does anyone remember? 4 megabyte. So the mmap you are calling using in lab 5 and 6 is creating an anonymous mapping. You're not doing any I/O. Your intention is to create a virtual, create a mapping in the virtual address space and use it as a heap for programmers, the data structures that the programmer is going to create. Sorry, today's a very bad day. Different operating systems do different things. Some do padding of zeros, some leave it to you. So it's not a behavior that is well defined. Some actually, I don't know any operating system that actually shrinks the mapping without letting the programmer know something. Right. So this is an area where you actually need to, what happened here? Hmm. Oui. Can the online students still see the slides? All right. Sorry, the system doesn't like memory mapped IO for some reason. It's a little bit tricky. So lab 6, when you return after the break, there's a very elaborate lab where you will explore all these things. So far we have looked at how to create virtual memory areas, how to create new VM areas in the virtual address space. The next question is, and this is something you're doing in the labs, how to manage when you have an area in the virtual address space. And one of the reasons we want to do that is dynamic memory allocation or dynamic memory allocators. Programmers use dynamic memory allocators to acquire virtual memory at runtime. Physical memory is entirely the responsibility of the kernel. The user programs, the programs we write, we never actually deal with physical memory, physical addresses directly. This is responsibility delegated to the kernel, but we, as user programmers, program writers, are still responsible for acquiring virtual memory and managing it. Now, we could leave it to the C standard library, or we could write our own allocators. Why do we want to write our own dynamic memory allocator? Sometimes we want to customize it for our special applications, and it makes up for a good assignment. Okay, so all I want to say is that this is what you're doing in the labs. For data structures whose size is not known at compile time, when you're reading input from a database, when you're reading input from a keyboard, you don't know how much data the user wants to enter. So when you're compiling the program, you can either have an upper limit, you can create a very large array, assuming that the programmer will never input more data than what can fit in this array, but this is a waste of space. Or you can use dynamic memory allocation, where programmers ask for memory as on demand, as they need it. And this is very flexible, very powerful. There is a break pointer maintained by the kernel, which points to the top of the heap. The heap grows upward in this direction, and the stack grows downward. Dynamic memory allocators manage an area of process virtual memory known as the heap. Now, there are two kinds of allocators. Allocators maintain heap as a collection of blocks, which are either allocated or free. And these blocks are given to the user program as requested. There are two types of allocators, explicit allocator, implicit allocator. Explicit and implicit is used at many places in computer science. So don't confuse it with explicit list or implicit list. Okay, an explicit allocator is where the programmer is responsible for both allocating and deallocating or freeing memory, virtual memory. This is called an explicit allocator because the programmer is explicitly responsible for freeing any allocated memory. Programmers are okay with correctly using malloc. They are okay with allocating memory properly when they need it, but historically they are not good with freeing memory. They either forget, or they provide the wrong pointer, and this is a source of many problems, many bugs, many security bugs in all of the software that we use today. And this has been a problem with C for a long time. And C is called a language that supports manual memory management. The programmer the Linux kernel is at this point 27 million lines of code. When you write 27 million lines of code, you forget things. You are not always on top of your game, and you forget free. When you forget to free memory, there are leaks, there are memory leaks, and there are other vulnerabilities, which when you will go to take software security and network security, you will learn more about it. So they came up with languages such as Java, ML, Lisp, Python. This list is growing. Scala, Go, Ruby. Don't use Ruby, no. Actually, they relieve the programmer from manually freeing memory. They have something called a garbage collector. Which is also called automatic memory manager. And together, the allocator and the garbage collector, we call it implicit allocator. This is where the programmer allocates virtual memory, but the programmer is not responsible for freeing virtual memory. A special piece of software called the garbage collector runs in the background, and it automatically, using proven techniques that accurately, precisely free all unused memory, that piece of software on behalf of the programmer automatically cleans up or reclaims all the unused memory. So the programmer is not responsible in languages such as Java and Python to manually figure out which portions of the memory are free, and not responsible for calling something like free. And this has led to a lot of, safe and secure programs and software, and the programmer's productivity is improved. Programmers can focus on the business logic or whatever they're writing, and they don't have to worry about this low level, what memory I need to free, what did I allocate a while ago, what do I need to do? This gets really complicated when you have millions of lines of code. Implicit allocators have a high overhead. So one criticism of these Java in particular is it's too slow. And takes up too much resource intensive. And the problem is that nothing in the world is free. And these garbage collectors that are running in the background, they are freeing unused heap space. They do a lot of analysis to figure out all the work that the programmer was doing. The garbage collector is not doing it on behalf of the programmer. And that takes up a lot of resources. So that's why don't run Java on a system which doesn't have enough resources. It has been a problem for a long time. So it's implicit because the collection or the reclamation, collection, freeing of unused heap memory is automatic or implicit. transparent to the programmer. Programmer doesn't need to care about what's free or not. They just need to allocate objects, and someone will take care of all the cleaning. And you can imagine that this practice has encouraged programmers to create a lot of garbage. While compilers also takes up resources, right? You have to compile something, but it just doesn't happen at runtime. There are languages where you're compiling programs at runtime, and they take up the same resources. Anything automatic will take resources. It's just that garbage collectors actually run at when the program is running. We will mostly talk about explicit memory allocation, and this is what your assignment is, and this is what you're doing in the labs. So malloc, there's a size T type, which we explain in the labs. You allocate size bytes. This is the interface, and then free. So you need to implement both malloc and free. And P should be a valid pointer that comes from malloc or realloc. Realloc is when you want to change the length size of the block of memory that you requested earlier. Calloc is the same as malloc, but it returns you a zeroed block. Zeroing is kind of important when we write programs, because programmers often check if a specific variable or a specific location is null or zero, and then they take an action based on that. If something is already there, it's first of all not secure. It may be the data belonging to someone else. There are vulnerabilities that exploit to that extent. And it's just not a safe practice. So zeroing will come up often in our discussions. Operating systems try as much as possible to return you pages that have already zeros on them. So in the labs, we are using mmap, but classical way to acquire more heap memory is using the sbreak system call. Today we use mmap mostly. So sbreak is a pointer that points to the, so break is a pointer that points to the top of the heap, and we can use sbreak to move that pointer to get more memory. So here we have malloc. This casting is not important. It's for readability. But if you cast it, if you later on cast P to something else, then it becomes important. Okay. So if you have a pointer P and you have a pointer now, this casting is important because you want to use P as pointer to a character and not pointer to a integer. Okay, I will give the answer tomorrow, but can someone tell me what is the danger in casting a integer pointer to a character pointer? Think about it. It's more subtle. Let's do this tomorrow. I'll give the answer tomorrow. Think of all the things you learned in Comp 2300. The important thing is that a pointer could be of any type. The way we explain it is a pointer wears a special glasses with a special color. And whatever is the color of the glasses, it sees the world through the lens of those glasses. If it's an integer pointer, it will see everything as an integer. If it's a character pointer, it will see everything as a character. If it's a pointer to a struct, it will see everything as a struct. Whenever you do +1, it will increment by whatever is the size of the struct. So you can take the same pointer and make it look at the world in a different way using casting. At one point, the pointer is seeing the world through special, whatever glasses, blue colored, and seeing the world as blue. And you can do casting to make it look at the world as red, right? Okay. So I hope that this is all covered in the labs. Here's an example of, so here are the assumptions. Free blocks are white and checked blocks are shaded blocks are colored, and forwards, and okay, I'll talk about it. So initially we malloc 4 words, whatever this is, words or bytes. Right, 4 words. We then allocate 5 words. We then allocate 6 words. And when we free P2, we free in the middle, this block in the middle. And then we allocate 2 words here. So we have 2 options. We could have picked either block. It's a matter of policy, what block the memory allocator returns. And this is where things are interesting. Which block to actually return to the user. So once again, you initially allocate 4, then you allocate 5 more, then you allocate 6 more. These are different colors. Then you free from the middle. This pointer has to match this one. And then you create, allocate 2 more words. Applications can issue arbitrary sequences, a sequence of malloc and free requests. And a free request should be a malloc block. So this is all the things that you need to check when you write a memory allocator. Allocators are difficult to write because of a number of reasons. You can't control the number or size of allocated blocks. This is all, it all depends on what the user wants. And allocators are typically on the critical path. It's very important to return something to the user as soon as possible. You cannot wait a long time to, so any heuristics you use should be very lightweight. You cannot do a lot of analysis in your malloc implementation. You have to be really fast. Imagine a data center application that gets a request from a user. For instance, when you use Gmail, right? How much do you typically want to wait for everything to appear? Or when you're doing a transaction on Amazon, you don't want to wait for 5 minutes, 2 minutes, not even 1 minute. There are response time constraints, and applications do malloc a lot. So backend application, if it spends a few seconds in giving you a block whenever the application wants it, this will really kill the response time, and users will not be happy with that service. So malloc, remember, is always on the critical path. You have to be very fast. You want to allocate blocks from free memory, which means you need a way to figure which blocks are free. The one data structure you have looked so far to figure this out is called what? Implicit free list. What is the problem with implicit free list? Whenever you want to allocate something, what do? You go over, what do you go over? All the blocks, those that are allocated and those that are free, right? This is not the best way to do it. I should only be iterating over my free blocks. I should not be iterating over all the blocks, right? We'll see what we can do about that. We need to care about alignment. We can only manipulate and modify free memory, and we can't move the allocated blocks once they are mallocked. Once your memory allocators are full of heuristics. You will, when you do the assignment, you will realize you have so many choices, and you will say, hey, I can do this, I can do that. What should I do? And that's why benchmarking and everything is important. There is no definite answer. It all depends on what the user is requesting. Big blocks, big objects, small objects. Some allocators are good for one type of object, some other. Why? So once you come up with a strategy to manage your heap and you manage your, like in the previous example, we decided to return for P, when the user asked for 2 words, we decided to return this and not this. Once you return something to the user, you cannot then do analysis in the background. Hey, I made a mistake. You know, I can do things more efficiently. Let me return this block instead. Let me do compaction. Let me do something similar. Why is it a problem? Because once you return a pointer to the program, to the programmer is going to use that pointer. It's going to write something to that block and then later on read. You cannot decide in your background, you know, let me change that pointer to something else and give that, you know, something. You cannot do these kind of things. Now, these are exactly the kind of things that automatic memory managers are really good at. So garbage collectors can actually do these kind of things, compaction and all that in the background. And they can take care of updating all the pointers everywhere, and the programmer will not even know. Java, huh? This is an advanced topic, garbage collection. We probably won't touch upon that, but I just wanted you to know that. They stop the application for a while and they update all the pointers everywhere. They do the compaction, and when they restart the applications, programmer doesn't even know what happened. That's why we don't write performance critical software like the kernel in Java, right? Because we don't have time for these things in the kernel. So we really care about throughput, and we really care about peak memory utilization. And these two are at odds with each other. Once again, this is something you will learn if you do the assignment well. Throughput is how many requests did you complete per unit of time? Which of the 2 allocators you have written in the lab you think have better throughput? The mmap-based allocator or the implicit free list? Which is faster? Intuitively, which one is doing less work? Why? Why do you say implicit free list?
mmap is really like slow stuff. You have to call it canal.
In implicit free list, you're iterating over a number of blocks. In mmap, you're just making one function call. So intuitively, mmap should be faster, right? All right. So there is a trade-off. But mmap is not very space efficient. It's not really managing the space very well. And when you want to manage the space very well, when you want to merge the blocks together, when you want to keep very large chunks of virtual memory together, you need to do some work and you need to do some analysis. So efficiency or memory utilization is at one end, and throughput, doing something really fast, is at the other end, right? And we will see that in our later. Okay, this slide is just saying in a fancy way that you have the total heap that you're managing, and you have the payload, the useful data on the heap. Metadata and padding for alignment are all things that are an overhead. That's not the actual data that the user is interested in. This is just for management purposes. What are some examples of metadata when we write allocators? the header, the size of the free block. So we typically have a header, and then we have the payload. And this header has the allocated bit and the size, not the bit, allocated Boolean or whatever you have used in the labs, or the size of the block and all that. All this is overhead. And for alignment purposes, sometimes we need to do something special, add some padding or add some blocks just for alignment. All that is overhead. The goal of a good allocator is to maximize heap utilization, make sure that most of the heap is used for payload and not for padding and other stuff, and to maximize throughput. So poor memory utilization is caused by a phenomena called fragmentation, which comes in two forms, internal and external. Internal fragmentation occurs when the user requests n byte block for a data structure or a bunch of variables or whatever, and we need to add metadata and padding for alignment purposes. So padding for alignment purposes, policy decisions to return a big block to satisfy a small request. At a high level, when the block that you are using for a specific payload is bigger than the payload. So this is the size of your payload. This is the actual data that you care about. And for some reason, you need to have a bigger block. It could either be alignment, it could either be because you have a lot of metadata, or it could just be the policy of the allocator. There is nothing left on the heap. There's only one block left, and that block is returned or used for whatever the user asks. So internal fragmentation is when the block is bigger than the payload, when the block is bigger than the actual data the user wants to put in it, or when the block is bigger than the request size. Request size. So program request allocate request size. Let's say that the program or the programmer requests a allocate size. Hey, give me 4-byte block, and for some reason you return a 16-byte block. So this is internal fragmentation. This only depends on the pattern of previous requests. So every time there's a request, you have a fragmented block. This doesn't depend on future requests. External fragmentation is when otherwise unused memory cannot be used to satisfy or fulfill a request. So here we have a malloc 4. So we allocate these 4 words. Then we have malloc 5. So now we have this space taken away. Then we say malloc 6. We only have 2 words left. We free P2. Okay, we free 2 words here. Sorry, not 2 words. We free P2, so we free this. Okay. Now tell me a request. Tell me an argument of malloc which is problematic. Yeah. That's a bad question. Let me ask it in a different way. Okay, an argument that can still, for which we have enough memory, but we still cannot fulfill the request. So at this point, if we have a request for malloc 6, then we do have enough unused space on our heap, but we cannot fulfill malloc 6 because we don't have it contiguous. So this is an example of external fragmentation. When there is enough aggregate heap memory, but no single free block is large enough. So external because it's not within a block, but external to the blocks, across the blocks. That's okay, I asked a stupid question. Yes. Okay. No, they are really hard to manage. No, we don't have them. Then you will need to write a program just to remember an indirection table to remember where each byte is. Okay, so external fragmentation is measuring that is one of the tasks in your assignment as well. So implementation issues when we're writing memory allocators include, how do we know how much memory to free given a pointer? And you already know the answer. We need to keep some metadata about the size of each block. So when we get a pointer to free, we know how much we need to free. How do we keep track of free blocks? There's so far you have looked at implicit free list. And in the assignment, you need to do an explicit free list. Now, this explicit free list is different from the use of explicit here is different from explicit allocator. We're not asking you to write a garbage collector. What do we do if we have extra space when allocating a structure that is smaller than the free block it is placed in? To mitigate internal fragmentation, we can decide to split the block and to create a new block with whatever is left behind. We don't have to give the entire block to the user. So when the block is smaller than the free block, we can do something to mitigate fragmentation. How do we pick a block to use for allocation? So I think what you have done in the labs is first fit, right? You start iterating the free list and you pick the first block that is free, and we have best fit, next fit, and other. These are policies. These are policies. These are heuristics. These are not mechanisms. There's a distinction between mechanism and policy. And I will clarify that distinction later, but there's a lot of room for heuristics and policies in allocators. How do we reinsert the freed block? So this is not a problem with implicit free list, but when we have other data structures, we will need to decide where do we insert the free block. Should we insert it at the head of a data structure or somewhere else? So these are all the implementation issues we have to deal with. Okay, how do we know how much to free? We keep the length of the block in the word preceding the block. So we have a header. Each block we have has a header. And this header is an extra word for every allocated block. So here we have P0, 4 words, green, but we have the size, which includes the metadata size. So the block size, we keep the block size inside the heap. It's more efficient to store metadata inside the heap next to the actual data. So we keep a header next to each block. Method 1 is implicit list, where you iterate all the blocks, both. So this is, can I use the O notation? Do you all know that? Okay, this is O allocated plus free. So you need to traverse all the blocks. This is not very efficient. For each allocation, it's O in total number of blocks. Then we have explicit free list, where we will only track the free blocks. We will not track the allocated blocks. And then we will have segregated free list. And if we have time, we will do the blocks sorted by size. Implicit free list, for each block, we have the size and the allocation status. We could store this information in 2 words, but that's wasteful. So the trick is the following. So we have the payload here. and any optional padding if necessary. If blocks are aligned, then some of the low order bits are always 0. Now, this is a standard trick we use in system software in a variety of different places. I think in the lab, you're using a Boolean to store, this is the waste, this is the waste. And these are the kind of optimization that your assignment is asking you to now do. Now, if blocks are aligned at an 8-byte boundary, how many bits are always 0? The least significant 3 bits are always 0. If blocks are aligned at an 8-byte boundary, then your addresses are such that the least significant 3 bits are always 0. So instead of storing an always 0 bit, we can use it for allocated free flag. And when reading the size word, we need to mask it out. So alignment, once again, if you remember, alignment helps with a more efficient transfers across the cache and memory hierarchy. And if we ask you to allocate align at an 8-byte boundary, then you need to pick an address that is divisible by 8. And those addresses will have the least significant 3 bits. Zero. So we have the size here, size header. We have this header. So instead of storing the size only, sorry, I said something wrong. It's not the address we care about. It's the size of the object we care about. So if the size is aligned, sorry, if the blocks are aligned at an 8-byte boundary, then the size of each block is such that the 3 least significant bits are 0. Right? So if it's 8, it's 100. If it's 16, it's 1000. So when you store your size and you know that the least significant 3 bits are always 0, you can repurpose those bits for something else, right? In this case, you can repurpose those bits for storing the allocation status. Right. 8 has 3 zeros. So the 3 bits are 0, right? The least significant 3 bits of the size are always 0. And we can reuse those bits for metadata, right? This is a standard trick that we use everywhere. So use these bits for metadata. So this is our implicit free list where we have the sizes and the allocation bit. What is it? Allocated bit. And then we traverse all the blocks to find the free block. So the allocated blocks are shaded and the free blocks are unshaded, and the headers, we have the headers. Okay, and double word aligned. So here's a code that looks search list from the beginning and choose the first free block that fits. All right. And P is the pointer to the start. So while P is less than end, so what are we doing here? Dereferencing the pointer and 1. And so if this is true or this is true, keep searching. Okay, now what are we doing here? This is a condition that we're evaluating. So this is a bitwise AND operation. This is a bitwise AND, okay? So when we dereference a pointer, If the pointer is to the start of the block, what do we get? What is P pointing to? The header. What's the header in our case? The size. So P is pointing to the size. When I dereference P, what do I get? The n integer, the size. And I'm doing a bitwise AND with what? With 1. So what am I trying to do? I'm trying to extract the allocate bit, the allocated bit, right? The allocated bit. So we are trying to use masking now. So this standard trick to store the allocated block bit, the allocated flag as part of size, because we know that our sizes are aligned, our blocks are aligned such that size will always have the least significant 3 bits as 0. So we can reuse those bits for something else. But now we have to extract those bits. How do I check if a block is allocated or no? I grab the size and I do a bitwise AND with 1. This will either return 0 or 1, and it will tell me whether the block is allocated or no. This is a bitwise AND. All zeros and the least significant bit is 1. So you're trying to read the least significant bit, which tells you if the block is allocated or no. Okay, and then if the size is less than or equal to n, so this is already allocated. And this is checking if the size is too small for the request. The request is length. The request is length, and if the size is too small. Okay, so what are we doing here? So we are advancing the pointer. So we are trying to do first fit here. We're trying to do first fit. We will just grab the first free block that fits. And those conditions are telling us, while we are iterating over the blocks, if the block is already allocated, or if the block is less than the size requested by the user, which is len. And we keep doing it until we reach the end. Now, to go to the next block, we are doing this. Now let's focus on this. So we are advancing our pointer P. We're saying P equals P plus the size of the block, and we're doing a bitwise AND with -2. Anyone remembers what is binary representation of -2 in 2's complement? All right, let's do it with four binary digits. So this is 0. You take the 1's complement, and then you add 1, and you get all right. So what is this trying to do? Get every bit from the size header except the allocated flag bit, because that, if it is 1, it will artificially increase the size of the block, because that bit is not part of the size anymore. We are using it for allocated or free flag, right? So when you do this standard trick, when you do these standard tricks in C, when you're writing system software, look, we save space, right? This is how we write software in the kernel. We have to be very, very efficient. We can't waste memory. We can't waste, let's have another type. Let's have another object. Let's have another variable. No, you try to get as much as possible from every single bit. So here we did this standard trick where we know that the size will always be a multiple of 8, so we can use these least significant 3 bits for metadata. But now everywhere we have to do the masking, and we have to extract and eliminate the bit. We have to be careful, and this is one of your optimizations we're asking for. First fit, next fit is like first fit, but we start our search where we left off, where the previous search finished. And this should be faster than first fit. We avoid rescanning all the blocks that we scanned last time. And research suggests that fragmentation is worse. Now, memory allocators are full of heuristics. Many things are empirical. We run representative standard applications, benchmarks, and we learn about the fragmentation and all that. It is hard to reason mathematically why are we observing certain behavior. It really depends on what applications request and free over time. And then there is best fit. As the name suggests, we choose the best free block that can fit the requested block. So the fewest number of bytes left over, keep fragmentation small, it improves memory utilization. But when you are trying to be the best, there is a cost. Nothing is free. You waste a lot of time finding the best block that fits. And the best is here, which leads to the least degree of internal fragmentation, which exactly matches very close to what the user requested. And when you try to be the best, you waste time. I don't know. It's just you try to do more analyses. You try to figure out. It's not true in real life. When you try to do the best, you're not wasting time. Right? Try to be the best in your assignment submission. You're not wasting time. It's more like you run slow. Yeah. My English today wasn't very good. You run slower than first fit. All right. Okay, we have one more lecture before the break, and I'm just thinking how much. Okay, done. Tomorrow we'll start here. Would I do that?